Let's rock and roll. Ignite 2019. Okay. Go Maria!
So, let me get my thing up here. Okay, here we go. I want to talk to you about some of my favorite graphs. I had this math class like a year ago, and they really liked graph time at the beginning of class. And I realized that that was the only time they got news in class. And I was like, well, where are you going to get the news when this class is over? And they were like, well, aren't you going to send us the graphs somehow? And I said, well, how about I email the graphs to you? And they looked at me like I was old. So I opened an Instagram account for them, and I started to share graphs with them. And now it seems that I have a new and very, very strange hobby. So, these are a few of my favorite graphs. Cue the music, 1 second. And you can sing along if you'd like, please do. Bike steering angles and world Snapchat users, SpaceX rockets and Tinder date choosers, Netflix subscribers and Amazon staff. These are a few of my favorite graphs. Game of Thrones viewers and Pokemon players, Fortnite Twitch watchers and Spotify payers. Netflix makes content for viewers' behalf. These are a few of my favorite graphs. Electric autos and drivers of Uber, fall of the camera and yield of the tuber, Old Faithful eruptions at Yellowstone, adoption curves for my favorite smartphone, CO2 rise, Arctic ice, and robots taking jobs. I want students thinking about the cool trends, and then I avoid the sobs. Battery prices and women in STEM fields, declutter patterns and thickness of snow shields, number of countries that stop CFCs. These are the graphs that put me at ease. Mars radiation and UFO sightings, swing sets in motion and LED lighting, commerce and Black Friday deals. These are the graphs that give me good feels. Podcast subscribers and newspaper reading, Tesla production and time for bread kneading, plastic recycling growing too slow. These are the things I think you should know. Hurricane winds, increase in staff, drugs for not being sad. I simply remember my favorite graphs, and then I don't feel so bad. Gender pay gap, sorry, I forgot one. Loss of vertebrae. On some days I feel like the world needs a slap, but what it could use, good graphs. And if you should need good graphs in your life too, you can search for Graphs in the World on Facebook or Instagram and get your daily happiness dose of graphs. And I'll pass out cards at the table so you don't lose them and I run out of cards. Next.
All right, Jerry. Jerry's gone first for so many years. He asked this time if he could go second.
All right, let's pull up the full deck here. Slideshow. Here's the mic. Stay in the box if you can.
There we go.
Mathematics of love. We all know math is used in more places nowadays than ever. So let's see what mathematics has to tell us about love. So first of all, math and love are pretty similar, aren't they? I mean, here are the 4 steps in math. Understand the problem, identify potential techniques, choose the best one, implement, and check. Isn't that exactly what we do in love? Except the only issue is how do we check your answer? So before going too far, there is an element of sexism in this talk. There are various permutations of the boy and the girl. I've only chosen the first one. I only have 5 minutes. But the math is all the same. So please excuse the sexism. So let's review the golden ratio. We take a line segment at some point to split it, such that the ratio of A plus B over A equals A over B. We call that phi, the golden ratio. And phi is said to be aesthetically pleasing. So what does that mean? The golden ratio appears in quite a bit of Renaissance art and in architecture. This is Da Vinci's Salvator Mundi. But how does this apply to love and to people? So let me introduce you to someone. This is Jade. Would you rate her an 8 or a 9? Or maybe a 6 or a 7? But how can you really be sure? Well, of course, how can a math person really be sure? We'd measure her. And that's what I did. So I've measured various lengths and ratios of Jade's face. The main one is length to width. I've measured these others. There's 6 popular ratios. I averaged them. Jade comes out to 1.289, which is not very close to phi. Beauty is in the thigh of the beholder. Here are a few celebrities, both men and women. I'm the last one, JT. I'm at negative 9.7, didn't do so well. But Barbie did quite well. I've also measured non-celebrities, and then I've asked my students to rate the non-celebrities in 1 to 10, and I've correlated the facial measurements with the ratings. The R-squared is not that great, but that's what happens more or less. Plastic surgeons know about phi. Interestingly, so do makeup artists, and you can buy eyebrow stencils in phi ratios, and those would be phi brows. Now, choosing the best partner. Mrs. Bush is alleged to have said, "I married the first man I ever kissed." There's certainly something sweet about that, but the question is that optimal? So how do we choose the best partner? So here's the problem. Suppose this is me at a singles bar, and I'm with a large number of attractive women, and I want to maximize the chance that I'm going to walk out the door with the best woman, whoever I define best. But at this point, they're all attractive, so that's not part of it. So you need to chat with a woman to determine your preference. You're going to chat with them in random order, one at a time, and after chatting, you need to make a decision, either yes right away or no. And if you say no, you've lost your chance. So what is your optimal strategy here? Well, if you select the first person, you have a 1 in 100th chance, 1 over n rather. If you select the last person, it's 1 over n. But can you do any better? So it turns out the optimal strategy is look, then leap. You want to look at r minus 1 person and then leap. And what is the optimal r? It turns out to be 37%. This is the probability formula. It's not obvious, but if you take some time, you'll see how it works. And the optimal r turns out to be 1 over e, and that's our favorite e, which is about 37%. This is a quick example of how this works at n equals 5. There are, of course, 5 factorial combinations to this. In case 1, you'd interview number 3 first, then number 4, so on and so on. I've played with the numbers, and as the number of applicants gets larger and larger, you do approach this 37% or 1 over e. So that's the optimal strategy. The strategy also works with applicants over a lifetime. It's also called the secretary problem as far as hiring people. It works for parking spaces, apartment rentals, and so on. It's widely discussed in the literature. So love is irrational. We've used phi and e. This is a cardioid you get from polar equations. Don't forget to convert to radians. I often do. And of course, a logical question is, did I use the 37% personally? Well, this is my significant other in the audience. But I did not use the 37% in finding her. But we've been together 14 years. I love you, honey.
right, well.
So talk about hip, cool, and sexy. I'm not, but okay. So I want to talk about some of my favorite books in mathematics, non-textbooks, so we don't trample on any toes and whatever. And all of these, along with others, are on my blog. So if you're not reading the webcomic XKCD, I'm not sure you're a mathematician. He's a great books. This thing explainer, he uses 1,000 most common words in the English language to explain food heating radio boxes, what you might call microwaves. And if you've not read the manga series, there's a whole series over all different topics. It's comic books. And my daughters can't get enough of them. I'm practically gone broke buying comic books of math and physics for my daughters in particular. Hey, comic books in math class, it's awesome. A couple of what I call coffee table books, full color photographs, lovely articles. Basically, you can crank through one of these a day for the whole year and come back around if you want enlightenment and stuff like this in your life about math or just a quick read sort of thing. This is not an easy read for me, having grown up in the Deep South with a lot of other things. Did I need to read this? Yes. Was it easy read? No. And if you're on Twitter at all, you need to follow him. Very relevant, especially with the topics that our speakers have talked about and so forth, whatever. Boy, is this a rabbit hole. Martin Gardner's, every one of his Scientific Americans collection is on one CD that's searchable. I've not stayed up past 5 o'clock in the morning looking at these columns at all. Don't ask my wife. Yeah, it's a rabbit hole, both from the AAA. Also, talking about these two, they have ebook versions of this, which are a little more affordable than the print copy, which are searchable. Also, they're in a nice enough format that if you want to just quick glance through, skip the mathematics to get a feel, and then come back through, they're amenable to that. So a couple of nice, all scattering of topics. If you haven't heard about Stephen Strogates and his new book, Infinite Powers about Calculus, Joy of X was about a series of articles he wrote for the New York Times that starts with Sesame Street and goes from there. Highly recommend you read those. They're fabulous. Did you hear about the credit card and the problems with people in different credit scoring and stuff? They interviewed Kathy O'Neill, the math babe here, of weapons of math destruction, how algorithms are tearing up our world and separating us, intentionally or unintentionally. Her blog may or may not be safe for work, depending on your tolerance for language. Yeah, we've heard about hidden figures. As I tell my calculus students, you think my test is hard? She took a test where if she made one mistake, John Glenn dies. Don't gripe at me about my hard test. Okay? And The Power in Numbers is a great book, fairly inexpensive, all sorts of articles about both contemporary and historical women in mathematics. Speaking of women in mathematics doing work, these two ladies, Carol and Joe, are doing great work. You need to read these books to separate the fluff from the actual research that's out there. Like anything, a lot of fluff has popped up around this because it's popular. Keith Devlin was one of our keynotes back in Jacksonville. Mathematics for Education for New Era is about video games and how their ideas tie into education. And his other one was for his MOOC. Remember those? But it's actually a really nice introduction to mathematical thinking you can hand off to your students. Oh, baby. 52 card tricks, all based on mathematics. The index is actually searched by topic. So if you want a card trick related to matrices, a card trick related to permutations, etc., find me Saturday. I'm going to have a deck of cards. I'll show you my favorite trick out of the book. It's awesome. To be blunt, you're not a math teacher unless you've read both of these. No. It's a nice summary of all the current research in best practices in mathematics teaching and online teaching and pedagogy. I can't stress enough you need to read this. Obviously, this is referring to using the symmetries and rotations of the dihedral group as the best way to move your mattress in the bedroom. What else would it possibly be about? You know? Yeah, I went there too, so whatever. He came here, but this was on the list before I knew he was coming to talk. If you haven't read his book, I highly recommend it, not just because he's a math and football player, but because it's a really compelling personal story. It's a great read. His wife, now partner, is actually a professional writer in trade, so it's obviously there. If you're not reading Ben Orland's comic Math with Bad Drawings on the web, you need to. A mix of sarcasm, humor, and bad drawings to explain various mathematical topics. The books are fabulous. You can get them in ebook versions. For a while, he was actually selling an autographed version of it. If you haven't played the game Set, you're not a mathematician. It's a wonderful game. Yes, I've said that a lot today. A wonderful game that you can throw out on the table, and your kids will probably beat you at some point, and that's okay. And then it's a lot of fun. If you're not playing the which one doesn't belong, you need to, because the best part is you can give a correct answer for each one of these and have an argument in class. Starting at the top right, the only one with all right angles, the only one with the odd number of sides, the only one with no side the same length. I'll let you figure the hexagon out. So it's by Christopher. He's got a book. And by the way, all those little square thingies, those are cross-sections of a cube as you run down the main diagonal. Christopher posted that on his Twitter feed, and I stole it from him. So, and I'm done. Whoever's next. Not me.
Hi, it's the last 25. The M stands for meters. And I do crazy things sometimes, and I don't know why. I'm a swimmer. I grew up swimming, and then I stopped swimming for 25 years, and then I came back to swimming 25 years later. And so once I started swimming again, I took on this challenge. Why? I don't know why. I do things that scare me. And I put a picture of heights because heights often scare people. But the scary thing that I did was I signed up for something called the 400 IM. A 400 IM is 100 meters of butterfly, then backstroke, then breaststroke, and then freestyle. And honestly, I was terrified of the 100 meters butterfly. Not that butterfly. Another kind of butterfly. How many of you know how to swim butterfly? How many of you can swim butterfly? Right. So, I'm from Louisville, Kentucky, and we have the honor of having Mary T. Maher, Madam Butterfly, who makes it look easy. Oh my word, she is amazing and brilliant. And so butterfly is kind of a big thing. But what I want to pose to you is when you take on a really difficult challenge, how do you make it through? When it doesn't get easier, when you can't breathe. And I really kind of freaked out. My friend talked me into doing it. And I'm like, how am I going to get through? How am I going to get through those last 25 meters? When no one's looking, I would switch to breaststroke. So we practice. And it still hurts. You still can't breathe. Recruit others. So that's how I got into the 400 IM is someone said, hey, we're going to do a 400 IM after every practice. She's in the green cap. And she swims a 400 IM at every practice in the summer. And then be inspired. So the woman with pink hair is Joyce Voigt. She's 85 years old, and she swam about 5 more events in the swim meet than I swam. 100-meter backstroke, 100-meter freestyle, 50 free, 50. I mean, she was just amazing. I'm from Kentucky, so another very, very inspiring figure is Muhammad Ali. Float like a butterfly, sting like a bee. He didn't know how to swim. Look at this. He's in the water taking this underwater photograph that's really famous, and he really didn't know how to swim. Okay, one of my favorites, ask experts for help. Like, some people hire closet organizers. Some people hire math content experts. I had swim coaches help me with my swimming. Come up with a strategy. This is the mental work that I had to do to really convince myself that I could do it. For the last 25 meters, I was going to breathe every stroke, keep my rhythm, and count down to the wall. And if I didn't count right, I would go -1, -2, -3. I just kept on counting. And then push through the pain. Just that's the last thing. Either you've got it or you don't. How do you do it? So the 400 IM did not scare me at all. Once I made it through the 100 IM of butterfly, I knew I could finish because the next stroke is backstroke. And you're on your back, catching your breath. And who cares how fast you go? It doesn't matter. It's all about the finishing. And then when you finish, you need to take that moment to just celebrate. It was a huge deal. It was such a big deal. And my friends celebrated with me, and it was amazing. So Nancy's older than me, and she has been swimming the 400 IM for years. So then what's next? Once you finish one goal, then you have to, where do you set your sights? What do you do? So I swam 5,000 meters. And for me, I would rather swim 5,000 meters than run 5,000 meters. And just so you know, I grew up as a cross-country and track runner. Never knew there'd be a day where I would become a swimmer and not a runner. And so now I've set my sights on maybe swimming 10,000 meters in 2020. It's a scary goal because it's actually going to take about 3 hours, and I don't know if I can swim continuously for 3 hours, but that's what I do. I don't know. Somehow I must have gotten dropped, and I take on crazy challenges. William is the swimmer who took the pictures of all the butterflies, of all the butterfly stroke that we were doing. So what about you? What challenges do you undertake? What crazy thing do you take on? It's not all about work when you're going to redesign a course or flip a classroom or whatever you're doing. But what do you do to challenge yourself in some unexpected way? Thanks. John Oates, come on down. Your turn, John.
Thank you,
Thank you. John Oakes.
Johnny!
So, I have a little song tonight also, but I do want to give you a little background first about what inspired the song. So, I'm on sabbatical this semester, and some of you have seen this picture from the regional lunch earlier, but I am on sabbatical to get pictures of math applications that I see in the everyday world. So if I see a picture of tacos like this one, I can see lots of applications there. The tortilla is round, and actually I did have a calculus student one time ask me if she had to memorize what a circle looked like. So there you go, like taco shells are round. So this is a preview of my presentation at the end of the evening. So try to think about which one of these is the lie about email. So this is my Instagram account that will have pictures of math applications from my sabbatical. And as I was thinking about these math applications, I thought, okay, what's love got to do with it? But maybe I would put my own flavor on it of what's math got to do with it. So if you're wondering about what my musical background is, I am going to tell you. I had done backup vocals in church play in the 3rd grade, and I was in the 6th grade school choir, and I sang campfire songs at high school at summer camp, and I still occasionally sing songs in the car and in the shower and other places. So you must understand through the touch of your curves, make my graph react. You can sing along. Only the thrill of Y meeting X rectangular system. It's Cartesian. Only Descartes must try to ignore that it means more than a tableau. What's math got to do with it? Got to do with it? Math, but a career in engineering. What's math got to do? Got to do with it? Means a curve when a curve can be broken. You can see that an abacus works when graph paper's near. If I tend to look dazed, I've seen it someplace. It got cause to be. There's for it. There's a curve that fits. You do it for me. Ooh, what's math got to do? Got to do with it? What's math but a career in economics? What's math got to do? Got to do with it? Who needs a curve when a curve can be broken? This is the instrumental break, so the one that's being lie is up there. Bill Clinton actually only sent 1 email as president and not 2. So get your facts straight, Hillary. Alright, so there's your email fact of the night. I've been taking on a new direction, but I have to say, I've been thinking about my own protection. It scares me to graph this way. Oh, what's math got to do with it? What's math but a career in underwriting? What's math got to do with it? Who needs a curve when a curve can be broken? What's math got to do with it? What's math but a job and education? What's math got to do with it? Who needs a curve when a curve can be broken? Ooh, got to do with it, Ooh, got to do with it, Ooh, got to do with it, got to do with it. Who needs a curve when a curve can't be broken?
Louder, Johnny. You made up for it.
Did you put this in here, Fred?
Hey,
Okay, this is okay. This is not part of my slide. I sent it in an email.
It's an Easter egg.
I didn't know
Just
Fred
for
was.
you.
Okay, I sent that as an email reply because I knew I was going to have to follow John, and now I've got 5 minutes to get that out of my head. Okay, so memes are a very popular thing now. They're really popular on our campus. My colleague Sherry McCormick and I, we actually did a PD session showing our faculty how to make them, and then how you can use them in the classroom. So I chose for this one the Marvel because it's also a big deal on our campus. About 35 of us dressed up as the Marvel characters for Halloween. We had a great time. These first few slides, I've decided this semester, I put a PowerPoint of about 15, 20 of these memes together that I put on autoplay for the first day of class. And instead of going over the syllabus, I would just have these playing in the background. And then I had a project activity for the students to be doing. So when they got tired of looking at the work they were doing, they could kind of look up. And the second day of class, I did a quick Kahoot quiz about the syllabus. And they did surprisingly well, better than when I would go over the syllabus with them. So I found that these are good to use because they hit the point quick. A lot of students using social media are familiar with these. They may not all be familiar with the Marvel movies, but I think these set the tone early in the semester here. Now, some of these are important if you understand the reference. You know, following directions, they don't do too well. So if they're familiar with this part of the Guardians movie, I feel like Rocket sometimes trying to explain to the Groots in my class. Now this one I sometimes will put up in the classroom when they're working on a project. A lot of times they get bogged down on the details and they run out of time before they get to the meat of it. So I tell them, you know, don't worry about the little things. Get on to the big one. My colleagues will know that Nebula is my favorite character, the best one. And sometimes these are the ones I don't show the students. These are the ones I will share with some of my colleagues on days when I'm frustrated and I just need to vent. If I send them that, they know what it means. If it's a really bad day, they get this one. And these are usually after I've gotten certain emails from students, and I'll elaborate on a few of those. The one where they just make a completely bizarre math whatever. And it's not if they're trying. These are the students that are not trying, and they just send me something that looks nothing like what we've gone over, even though they have an example to do it. Then you get the email from students that just are not reading your directions, are not reading the syllabus. You know, I've been wanting to send this one, and I haven't had the guts to actually send it back yet. About this time of the semester, you get that email from the student, either in your on-ground or online class, who hasn't been there for a while and is trying to explain what's, who they are. And, I want to send this back because, honestly, sometimes I don't remember them other than a name on the roster. But the favorite one we all get is the email we get from the student with no capitalization, no punctuation, 4 lines of run-on sentence. And I don't want to be mean. I want to reply to it, but I also want to reply in an equally incomprehensible way. And I really want to use this one. One of these days I'm going to do it. I haven't done it yet. Now, on the positive side, I've used these for good purposes. I've had some students who will email questions back and forth and asking for help. And sometimes if they get it right and they're not sure, I'll send them this. I had one student who was really just on the verge of figuring it out. And we went back and forth one night over email, about 5 or 6 emails. She finally figured it out. And so I just sent this back to her. And she was so excited. The next day in class, she was showing this to the other students in the class. How cool, I was so happy. I gave an assignment one time, and I told Sherry, this is such an easy assignment. If anybody makes a mistake, I'm going to send this to them. And I didn't,
But sure enough, one of my top students made a careless mistake and missed it. And so the next day in class, I said, I almost sent you this as a reply. She said, oh, that would have been awesome. Next assignment, I'm going to make a mistake on purpose just so you can do that. Now, I'm going to finish with a couple of shameless plugs. Tomorrow morning, right after breakfast, Sherry, Arthur, and I have a session where we create QR problems. Specifically, tomorrow we're going to focus on Disney, Marvel, and Star Wars. If you're interested in that or just interested in coming up with problems outside of the normal textbook. And then at 2:15, if you're interested in AMATYC webinars, I'm the webinar coordinator. I'll be happy to meet with you and answer questions. And who's next?
So let's do a little math. I think we're light on math tonight, so take a second to try to figure out the error. Actually, you have exactly 5 seconds to figure out the error. So I thought tonight I would have an hour to speak. I'm a little confused right now. I suppose 5 minutes will do. So I'm going to talk about my sabbatical. I'm going to talk about an idea I had that helped me out, the aftermath, MFET for all, math for elementary teachers, and some final thoughts. So sabbatical. Who's on sabbatical? Who's been on sabbatical in this crowd? Just good. I held off for many years, 13 years waiting for my sabbatical. I wanted to finish my doctorate for my sons. My sons are 6 and 8 years old, so that's how long I've been doing my doctorate, unfortunately. I created a plan for my department and a few other things. I was reluctant to do this because I love teaching like everybody else in this room. I was very excited. I thought, well, it's time off from my routine. I could, just be lazy. It'd be fine. I'll get so much done. It'd be fantastic. This was the reality. Death every day, essentially. Drop the kids off at school, go write and write and write and write. I tried long hair one time. That didn't quite work well. It was just not a happy time. I felt very alone, isolated, exhausted, more tired than teaching. It just felt meaningless. Why did I apply for this sabbatical? I kept having doubts. I was going through withdrawal of teaching, withdrawal from my colleagues. I just needed something. And thank God I found an idea. It hit me. MFET, math for elementary teachers. Going back to my roots, I taught 6th grade for 2 years. A traumatic experience. It's taken me many years to get over it. I wanted to emulate my math heroes. I wanted to interact with human beings again. I ended up being little ones, unfortunately. So here's the story. My sons go to school, so I talked to their principal. And I thought, well, let me see if I can get in here and actually do some math with some people. They wrote me back, and miraculously, momentum started to build. Things were starting to happen. It felt really good. And so then it became a job, a very time-consuming job. I overcame my PTSD from my 6th grade teaching. There was a lot of it. I worked mostly with 3rd graders. It was essentially a research project, field notes, artifacts, 100 hours of work, tons of work. And then I got schooled. Kids are tough and germy and disgusting, really. So it was a challenge, but it was really meaningful for teaching these courses. And so the aftermath, the circle's in a funny place, not supposed to be there, is 240 different artifacts from their work, which if you taught the math for teachers, having examples of actual student stuff is really useful, really important. And here's some more examples of them. So just knowing what kids are doing in school beforehand was really useful. Trying to find that next Gauss. So that was the first problem I gave them, to add the first n numbers, and miraculously they did it in various ways. And I told the Gauss story, super fun stuff with them. The aftermath was that I created 13 different teaching scenarios that look like this for the Math 1, Math 2 courses, MFET is what I call them. And it was kind of a labor of love. Something I didn't expect out of the sabbatical, which was, whatever. Oh, here, crowd participation part. So there's some stories, lots of stories. I need you to shout out your favorite perfect square. Now, I know I'm in the right room for this, so please shout out your favorite perfect square. Okay, I'm tabulating them all right now. Shamefully, nobody chose 1, 2, 3, 2, 1. Really sad. Number 4, I'll say this. So there was a student who ended up in one of the enrichment groups. One of his friends said, "What are you doing here? You shouldn't be in this enrichment group." Who solved the problem first? The student that shouldn't have been in the enrichment group. So it was a really validating story for that. The aftermath of this is that connected me to the school. It gave me purpose in my sabbatical. It really saved my sabbatical because I was miserable, as you can see. And I got all this stuff as a result of it. It was a really, really neat experience to be able to do that. In addition to that, they want me back. I told them I'm working this semester. I can't come back. No, I can. I'm going to try to sneak in there. My wife's an elementary teacher, and so I get more empathy for her. It settled my parenting expectations. I kind of go off the rails sometimes. And then I've been able to use these teaching scenarios this semester. They fit into my classroom. They're my stories now. I've got something to share with my students. It's something I didn't have before. I was just kind of pretending, using other people's stuff. This is mine. And crazy enough, we're almost done. But MFET for all. If you're not teaching MFET, or you haven't been in an MFET class, you should be, because it's everything, in my opinion. If you're wondering why your students have trouble with something, it came from elementary school. We don't point the finger back. We think about what are they doing there. That's what MFET gets us. So my last little final thoughts are these are things that are in curricula right now. The top problem is one that you give to college students probably. The bottom one is, can you guess the grade? Can you see it? Third grade, which is really cool. Thank you.
All right, so these are things that I didn't learn in school that I thought were actually quite interesting. The third one's going to be kind of bizarre. The first two are actually reasonable. So here's the first. If A is the side of a triangle, alpha the opposite angle, ratio A over sine alpha gives you the diameter of the circumscribing circle. Actually, I'm supposed to get a picture here. This is not working. I'm sorry. Well, anyway, I had a little picture there of the bit. The corollary is the law of sines. If A, B, and C are sides of a triangle, opposite angles, alpha, beta, and gamma, then A over sine alpha is B over sine beta, C over sine gamma, because each of those ratios represents the diameter of the circumscribing circle. If you wanted to derive that for yourself, I suggest you start with the special case where the diameter is one of the sides of the triangle. And then after that, there's supposed to be another picture here, if that picture reminds you of things about inscribed angles, then you're probably okay. My biggest reason why this was curious is just that it isn't better known. I've not seen it in any trig books. And it gives this really nice way of thinking about the law of sines. And it also has a curious way of thinking about even Snell's law. Okay, the second triangle fact is this one. The area of every triangle is half its perimeter times the radius of the inscribed circle. Supposedly every math talk has one proof and one joke, and they're not the same. So we'll do a proof on this one. So you partition the triangle into 6 right triangles by connecting the center to each of the points of tangents in each of the vertices. And there's supposed to be an equation here. The area of the original triangle is the sum of the areas of the small triangles. The base and height of every right triangle, you can just use the legs. And in all of those right triangles, the radius is one of the legs. So you can pull out in half and the radius, and what's left over is the perimeter of the original triangle. And you might have seen this half a perimeter, semi-perimeter in the Heron's formula. It's hard to derive. The place where I saw that second triangle fact was in Euler's derivation of Heron's formula. He does one more trick and then everything pops out. So another place where this second triangle fact actually comes out is this useless fact that if the sides of a right triangle are all integers, then the radius is also an integer. Isn't that surprising? Well, anyway, you can prove it like that, but there's not enough time in the slide. Okay, not all polygons have inscribed circles. But if the polygon does have an inscribed circle, its area will be half the perimeter times the radius of the inscribed circle. And the proof's the same as the work for triangles. But in particular, this means that the area of every regular polygon is half its perimeter times the radius of the inscribed circle, which I didn't see anywhere else. And I thought this was amazing, astounding, and counterintuitive, but you've probably noticed that the area of a circle is half the circumference times the radius. All right, so for the final triangle fact, we have to review some calculus. So I have a thing up there for what a 0 of a polynomial is and a critical value of a polynomial. And the non-triangle fact is that the mean of the n zeros of a polynomial is exactly equal to the mean of the n minus 1 critical values. That's supposed to be popping up there. I don't know. Oh, so this one is, that in the case where n equals 2, you've got a nice picture in your mind. The graph is going to be a parabola. The zeros are x-intercepts. Yeah, the vertex is in between. But it actually works in the case where it's any old second degree because b minus b over 2a is going to be what the critical value is, and that's halfway between the two zeros. All right, so here is the final triangle fact. With a cubic polynomial, if the 3 zeros are actually vertices of a triangle, then the two critical values are the ellipses, the foci of the ellipse that's tangent at each of the midpoints of the triangle. Here's the picture. You've got the zeros are the corners of the triangle. find the midpoints of the triangle. There's only one ellipse tangent there, and the foci of the ellipse are exactly the two foci. So Dan Kalman calls this the most marvelous theorem in mathematics. If you want to find out more, Google his name with most marvelous theorem, and you'll find all kinds of nice stuff about it. All right, so I'm going to finish with a final thought, and it's actually a thought that was given by a student on a final exam. It's actually my wife's trig student. And so the student had on this exam a very nice little circle and labeled it unit circle, but also put on it not to scale. You can think about that while you wait for the next speaker.
How are your necks doing looking at the podium and the screens? And I apologize for that. I'm going to do 2 ignites in 5 minutes, believe it or not. The first 14 slides are on the first topic, and then we'll move into the second topic. But I just want to tell you that if you use publisher material or instructor-created material and you come up with fabulous instructional materials, it's just not enough to prevent students from feeling like they're on their own. And I want to tell you that not only for teaching online, but also on site, in class, face-to-face, your job is not to deliver content. Content is ubiquitous. It's everywhere. Here's an example of some of my favorite sites where you can find magnificent content. Instead, your job, teaching on site or online, is to create a sense of community. USC, famous for many other reasons lately, their biggest social work program in the country compared this new program of using synchronous activities like watching the Hollywood Squares TV show. I was also intrigued by an MBA program with a 96% completion rate. And what they used were synchronous activities, even though it was a completely online course. You will get pushback from both instructors and students, but they'll soon agree to the benefits of being able to meet synchronously with your instructor and your fellow students. It's also a way to contribute to regular and substantive interaction. You may be undergoing, as we did at Coastline College, an external audit by the DOE, the Department of Education, which said if instructor is not initiating contact and there is not regular and substantive interaction, it's going to be categorized as a correspondence course, and they want all their federal funding back. So we're talking about millions and millions of dollars. So one of the things that I do is have regularly scheduled webinars, and the nightmare is that no one will show up or no one will have any questions. What time of day is best for students? I mean, these are all the negatives that you can come up with. So here's what I recommend to create a successful synchronous activity in your online course. To divide the hour that you meet with the students synchronously up into thirds. And the first third, that just lasts 10 or 15 minutes, is focus on the affective domain. It doesn't have to be anything fancy. You just have to show them a little meme like one of these or a poster and have them type in the chat box or to unmute their microphone and share with the class. How do you feel about these posters? The second part of the webinar can be content. And you don't want to deliver lectures. You don't want to do anything that students will fall asleep to. Instead, you want to focus on the topics you know students typically struggle with. And you can also feel free to have them work collaboratively. And you can even leave the room during your webinar, which I often do. And then I come back and ask for a share out. And of course, at the last part of it, you can ask for questions. To help with attendance at these webinars, I convinced our school to list them in the schedule. So even though it's an online class, my section of college algebra with support says that you must be online every Wednesday evening from 7:30 to 8:30, and I'm getting a great participation. Okay, on to my second topic, which is to protect integrity in online math classes. This is becoming a very hot button issue, and it's mostly being forced somewhat by administrators, but also by faculty as well, who want to give online computer-based exams. Maybe they're not even proctored. There are proctoring software programs out there that claim to have AI to detect eye movement and head movement, to determine when someone's cheating. But let's face it, are you going to really watch all those videos? And what if the student says, dude, I was just looking at the wall clock. I wasn't cheating. Also, we want to have students show their work, explain their thinking, and justify their answers. A part of the reason administrators are giving us to justify this is that it's not an online class unless it's 100% fully online, and I say that's BS. To help me in the state of California, the state chancellor's office is coming up with 3 categories of distance education. Fully online, FO, partially online, which we think of as hybrid, or what we do at Coastline, which is instruction is online, but assessments are delivered that are in person and proctored at a flexible place and time. Our department came up with a statement enforcing the use of human line-of-sight proctors. Thank you very much.
I'm here to talk about power-reducing numbers. I stand here to promote white power, reducing formulas. Wait, the rate of my spoken words was not constant. There was a moment when the derivative was 0 words per minute, a critical point of my white silence. I want to talk about a Venn diagram that looks at the power-reducing formulas within mathematics and addresses the dominant powers within mathematics. What lies at the intersection of these two? You see, power-reducing formulas are often used in trig functions, a transcendental function that has reached a power way too high and needs to be reduced down to a linear combination so that the integration can occur. But your power-reducing number is way more than an integration of you do you. Yes, you be you. You be yourself. You be your best. But you have to be conscious of the powers that you have. I have the power of whiteness. I have the power of male. I have the power of a white male. Now, these powers can often go unseen, like when the exponent, the power, the degree is a 1. Or like when the leading coefficient is 1. But I now begin to see my own powers. And I want to take this to a quotient of 1 over 2. For every one of me, there's going to be 2 unlike me. You see, I want to get to the roots of my power. I want to square root my power. Time out. Can we just talk about not always using the word square root? We can say 25 to the half power instead of just saying square root 25. Why do we have such a problem with acknowledging power functions? I have the power of whiteness. I have the power of male. I have the power of white male. Another type of power is mathematical knowledge. But who do our students see with this power? Who has the power of a mathematics genius? Well, often it's somebody that looks like Albert Einstein because of all the quotes that we see at the bottom of our syllabus, the quotes within our emails, the quotes within the textbooks, the pictures that are in our textbooks, the posters that are everywhere. But I'm bringing the Einstein power-reducing formula. For every 1 Einstein, I'm bringing 10 Katherine Johnsons, 10 Kelly Millers, 10 Emmy Noters. When we reduce the powers of others, we make space so that others can exist. What do you notice about these 12 names? What do you wonder about these 12 names? Well, you see, these are the 21 women out of 512 people that have an Eredish number of 1. Now, I don't think this tells a story of Eredish, but more about the dominant powers within mathematics that we have to address. So I'm asking you today, what is your power-reducing number? What separates you from people that are reducing the powers? Do you understand your degrees of freedom? Toni Morrison eloquently says it like this when he tells her students that when you've been brilliantly trained for the jobs that you have, just remember that your real job, that is if you are free, you need to free somebody else. And if you have power, you need to empower somebody else. This is just no grab bag candy game. We are making an impact on mathematics, but we have to use an equity lens to understand the powers within prowess. You have to understand the power within proficiency, the power within ownership, the power within engagement, the power within student success. I'm trying to make my power-reducing number 0 because I believe that if we all have a power-reducing number of 0, this is finally when we are all 1.
Let's take a 5-minute break from fun. So, yeah, there's really no fun. So partial fractions, let's see how can we, well, with a proper rational function, well, this is fun. And then the degree of the top part of the top polynomial is less than the degree of the bottom, and we wish to integrate, and we do it using partial fractions. So if we have linear factors, all distinct in the denominator, we're going to have a linear combination of their reciprocals for partial fraction decomposition. And this is too long, and maybe I should say like the previous people. Okay, if they repeat, if the factor is raised to the power of r, for that multiplicity, you're going to have a linear combination of all the powers from 1 through r. And blah, blah, blah. Okay. So irreducible quadratics, we are just going to have for each one of those, we are having a linear term at the top and the quadratic at the bottom. And when they repeat, when they have multiplicity, again, it's going to be now a sum of linear factors divided by the quadratic to various powers. So we know all of this. This is nothing new. And what are our strategies? So first we factor the denominator, we write our function as a sum of partial fractions, we multiply both sides by the denominator, and in the outcome we solve the system of equations to get the coefficients. The usual method, the one that we find everywhere, is the undetermined coefficients, or the method of Adams, where we compare the like terms, we set the coefficients equal, and then we solve. Another method which really works in engineering is the sample method. It's fast, the plug and chug method, where we set certain suitable values of x, and then each one of those yields an equation, and then again we solve. So let's see an example. In this example, again, we multiply by the denominator, we look at the like terms. That gives us coefficients. A is 4, C is -7, B is 1. Well, let's look at our suitable x. So if we choose in this same example x to be 0, that gives us A is 4, and then you pick a complex value, x equals I, which is going to give you 2 coefficients in the same step. And you can do similar things with integrals. So if you're looking at this tedious integral that students really love when they have to do 2 steps of integration by parts, you can use complex numbers. So for example, it's based on Euler's formula, which allows us to split this exponential into a part that contains a cosine and a sine, which breaks your integral into 2 parts, a real and imaginary part. I hope you didn't see the typo. So then, well, you just keep solving. You multiply, so you solve as an exponential, you multiply by the conjugate, and you break it again into 2 parts, and those are your 2 parts of the solution, the real and the imaginary part. And okay, so that's, enjoy the beauty of the solution. And so, as John Derbyshire, the writer, says, with complex numbers, we can do anything.
Am I ready? No.
It's standing in the blue tape.
Oh, God. You know this is going to be hard for me to stand in the blue tape. It's not me yet. Those are not my references. Okay, here we go. This is me. So, an ode to math and golf. So, my name is Mary Menard. I am the AMATYC Traveling Workshop Coordinator. That's my plug. So, just wanted to throw that out there. This is an ode to math. Now, don't worry. I'm so glad I decided not to sing because, yeah, I've had enough of that. So, I also want to throw out, I've been on a sabbatical. It's the best, but what's better is banked leave. Just saying. If you don't know what that is, I'll let you know. So, math and golf. If you've ever played golf, you know the frustrations of golf. Anybody? So, yeah, we're just going to do like a love-hate relationship as it matches with math and golf. So, as we all started our math careers, I like to say, we started counting. Hey, 1, 2, 3, right? Just to 18, not a big deal. No big deal. So how does this come into play? Well, if you've never played golf, you know there are 18 holes in golf. After the first hole, this is about what you look like. So this is my baby, my cat. This is Pistache. So I had to put her in it because this is exactly how I feel after one hole. So then I bring in some addition. So with golf, most of the time I'm adding, unfortunately. And I'm not subtracting like I should. But yes, adding is fun. I'm not a fan of it. I always tell my husband that, and of course he laughs and messes with me. But it doesn't matter when you play on a place like that. I don't care. I'll add up to 100 because that's usually where I am. So the key for me was always having fun. Every once in a while I get to subtract. Here, my subtraction is the weather. I am from Texas, so this is a little bit of insanity for me. I saw the weather temperature one time. It said it was going to be -5 for the high, and I was like, what? So the best thing is when your ball, of course, goes in the hole, especially if it's a birdie, which I've made. Never made a hole-in-one yet. An eagle would be like the best. If you don't know what those are, I'll let you know later. Slope in golf, does it come into play? Ugh, yes, you can never see it on TV, but if you are a true golfer, the slant of those greens just drive you nuts. So how does this ball not roll down? Do you see that slant? There's just no cause for that. There's like a nice little thing of grass just right down below that, you know? Oh, and look, linear applications in golf. Could you imagine? What could they be? So lines, right? How would we do that? Okay, here's one. My husband, when he hits a ball that unfortunately doesn't go very far, but he can swing that club and throw it further than the ball actually went. Now, of course, it's linear because he hurls it from the side. So quadratics are big time in golf. You can get that one perfect model, so you can have that nice quadratic that's going up, or you could have the under variation. So I grabbed this one. If you were in Orlando last year, I love this picture. It's not really golf based, but I just loved the picture. So I had to throw it in there. But here's my golf one. So 3 balls, none of which are on the place where they're supposed to be. But look at that lovely quadratic that could model those 3 balls. I mean, that's just perfect. It's just set up to be modeled. And I just put that on there. Now, what are the further applications of this? Well, so you see a golf cart, right? I love being the driver of the golf cart, right? And it's because, you go uphill, you go downhill, you get your friends involved. And whenever I drive, inevitably this is some of the reactions. So the foot is on the, help me, save me. And then, of course, she's giving me, it's really not that scary, but yeah. And then finally, of course, this is my husband and I. We love being able to get outside and seeing views like this. It's just one of the best things. And so bringing this home, I heart math. And of course, golf is just right in there with it. So thank y'all. Up next.
So I like golf too, and we'll have to get together sometime. We golf even in the snow here in Wisconsin. I'm going to talk to you about things that you see, and hopefully you'll be amazed at the way that you can solve problems. Mixture problem is nothing more than weighted average. Solve it on a fulcrum. Done. That's an intentional pause. You throw the words more than or less than in a story problem, oh my goodness. Suddenly all reason leaves the brain. Draw a picture. You see the solution right away. Here's another one. 15 gallons fill a tub, 2/5 full. My students will do everything with that 2/5 and 15 that they can possibly think of. But if they draw the picture, they'll get it right. Baking problems. They tell me they like baking problems, but not when I say it's 1.5 batches. A double number line solves that problem really slick. I think this next one I have a little problem with my picture, so imagine it. It should be there sometime. And you've seen students work on this problem. They don't know what to do with that 1/5. They subtracted from 44. All right, well, you might have saw the picture. Well, here's another problem. This one has a box of chocolates. You eat some, you eat actually half the chocolates, and then you reweigh it. I don't know why, but you do. And here's a couple of solutions that don't require you to write an equation. And they work pretty slick. And students can do these fairly fast. And then we'll have the solution that you'd see in many books with a system of equation, but I think that loses so much of what the other solutions tell you. I would say that would be inelegant. Oh, here, I love O snare. Fly out of there all the time. So some of you may be leaving tomorrow at noon. Let's figure out whether you'll take off on time. How many of you saw a tree diagram as soon as you read that? Conditional probabilities, you see a tree diagram. It's beautiful. It's a really good way to look at that problem, rather than writing out the rules of probability. Well, here's another way. An area model solves the same problem, just from a different perspective. That's one of my favorites. I like the area model. It has its limitations. It's only two-dimensional. You could also solve this using a Venn diagram. So the Venn diagram doesn't get used as often as the tree diagram. Doesn't get used as often as the area model, but it's still usable. But more importantly, I want my students to be able to take all 4 representations, I didn't show you the equation one, and connect them. See how those numbers appear in every single one of those representations. So our next problem is a problem that my students stop reading after about the 5th word. And it's a classic problem. You see these all over the place. You can't pick up a pre-algebra book or an algebra book without seeing a problem like this. Well, here's the solution. You got a task, somebody does it in 100 minutes, another person 120, you don't know about Lou, together is 40 minutes, so write the fractional parts that they work on, and you've got the problem solved. Well, here's my favorite problem. I did this one in San Diego, talking about visualization in math. The computer died right at the very beginning of the talk. So everybody read this, and then I had nothing. So I was going to show them this beautiful representation that solves the problem very slick. This was a group it was a joint AMS MA meetings in San Diego. So I have all these mathematicians writing like crazy trying to solve this system of equation. And here's what I did. I went to the back, I saw a water cooler, I picked up the cups that were in the back, and I used 4 chairs. I laid it out here on a a board, but I used 3 chairs and solved the problem using cups. Here's the system of equations. It's a mess. So my students, I encourage them to look at things a little bit differently and then ask, did you see that?
I had about 3 beers. The Vikings just fumbled the ball, and I got an email from Fred. So that's kind of how we started this. So analogies, studies out there, they show that analogies don't really work to help us learn, but I don't really care about that. I cared about, that really gets the kids in the class ready to learn. That's what they did for me. And so they create the relationships that give the students in class. I came from that 7-12, so I knew that it worked, but they just didn't know enough to work all my analogies. So I was really nervous about doing this talk, so I asked my wife, what should I do? They said, show them you can do some math. I multiply. I got 6 kids. Okay? So basically, I'm from Minnesota, and so my main story here is that this is what it's usually like. And we went on our honeymoon, and we went down to the Bahamas. It was great. Okay, and I tell the students this, I tell them in class, I tell them it was great. We went down to the Bahamas, but I was not allowed to go there because I did not bring a pair of pants. I was not allowed to go into the restaurant because they would refuse to have someone in the restaurant without pants. Why would I have a pair of pants? And so I started to use this analogy to help students understand that we got rules. We got rules here. And those rules are basically like, well, there's either McDonald's or there's Olive Garden. You can go into McDonald's without a shirt on and they're still going to sell you a Big Mac. I guarantee it. No shoes? Excellent. Olive Garden, it might be a little bit different. And because we have McDonald's, I took this graphic. I always like to order the Primo number 1. I order a Big Mac, fries, and a drink, and I'm always really ticked off when I get a drink, a Big Mac, and then the fries. Social media is going to be lit about that. Fractions and word problems, students run from them. They hide from them. Exactly like, I ran and hid from left-handed layups. Students really like that one. They really think it's hilarious. Big Al was, he was a super senior is what we called him. He sat in the back right corner of the class, and I used to use this anytime I dealt with counterexamples. And I said to him, well, never mind. I thought I had 2 slides for that one. This is for don't end it in a roadside ditch. I love this for talking about conditionals. Okay, let's talk about toasters. Why is a toaster a function? Because it clearly passes the vertical line test. Okay, but be careful with the domain of functions because I always struggled with that. Because I would get to these things like this, and I said hot dogs weren't involved, and then crap, and then eggs. Really crap. So help me, guys. Help me change the world. We need a toaster that does steak. What's this? The composition of functions, that's right. Okay? Absolutely. Students really, really get it, especially people who are doing laundry for the first time. Speaking of doing laundry for the first time, I folded these last week. No, I didn't. I'm not one. But here's the inverse function. Should be coming up any moment here. There we go. I absolutely love the point slope. And so I talk about slope-intercept form is just a hot rod. It's got to run on a premium. But then we got this station wagon. Everybody's like, what's a station wagon? That's a station wagon. All right, we got crying kids. If anybody loves probability, you know that taking them to these sticker machines is awesome. Okay, but in Minnesota, this is the only thing you get out of them. I gave this to my trig class the other day in a box, and then the other side of the room, I gave them this. Well, there it is. Both groups did not work with the same enthusiasm. And this is the mother of all analogies. This analogy right here fixes this problem. This is phenomenal. This is unbelievable. You'd never imagine what is going to go on with... Oh, never mind. I'm done.
Hi. I love my students' brain enough to spend my postdoctoral research on the development of their brain. When I'm stepping in my classroom, I know that I have to convince my students what I'm telling you worth your time. And there is something in it for you right now. A Harvard study focused on 80 hotel mates, dividing them in two groups. The control group didn't learn anything. The informed group learned about the benefits of physical activities in their job. Their health indexes were measured in the beginning and end of the study, and the people who were informed, they lost more weight, they had lower blood pressure, and they were more satisfied with their job. Our brain is very similar to our smartphones. It has the hardware, software, and reception, and we can even upgrade our brain the same way as we are upgrading our smartphones. But there is one catch into it. It has to be done during the young adult brain. While we have our students in our classroom, they are losing half of their brain. It's nothing bad. Which part they are keeping, which part they are losing is important. And the principle behind it is use it or lose it. And we have technology. It hasn't changed only our outside world. It has changed the interior of our brain. The Maslow hierarchy of needs has Wi-Fi and battery life as the base of it. Our students need the information and they get a lot of that. But what they need to know is information is not knowledge. In the process of changing information to knowledge, our brain is going to be upgraded. Our brain has plasticity. That means it changes its neural pathway as a result of experiences that we have. The senses is going to be completed earlier because brain plasticity has timing, and timing is everything. Motor skill and language comes next. That's why I have the accent. I learned English in my early 20s. And higher cognition is when we have our student in our class. They can become the smartest that they can. Our brain is 200 billion cells at the time of puberty, 100 billion later in late 20s. It's not the number of cells, it's how they are connected to each other, which is important. Amygdala, which is the reactive or fight or flight part of the brain, is fully active and in charge during the time that we have our students, young adult years. This is the part which is okay to be lost. The prefrontal cortex is the part which we want to keep it through the logic behind the mathematical formula that we are teaching them. When scientists placed an adult and a young adult into MRI machine and asked them to think about the same topic, they saw that adult users prefrontal cortex versus teenagers using the amygdala. For the same input, we have different outputs. What is in it for them right now? If I could have put them inside MRI machine, I could have shown them how many more connections they are making in prefrontal cortex in my math class. As an electrical engineer, I learned that every single electronic component needs a power supply. Blood flow is the power supply for our body. And when it comes to brain, it requires 3 times more blood flow than any other organ. If we look at these brain images, activities like exercise and meditation increases the blood flow, and diseases like depression or Alzheimer decreases the blood flow. Look at these two and see some similarities. Our student would love to have that increased blood flow and increased attention. But to what price? Many of our students taking Adderall without doctor's prescription during the test to increase that blood flow. Our very smart students have very low span of attention, even less than a goldfish. Look at the complexity of our brain versus goldfish brain. It's a loss to lose it to them. This is the time that we can help them to better understand their brain and care about their brain more than their grade.
Hello. My name is Eddie Churchian, and I'm just another John Oakes wannabe. Since we're here in John's place, his home, and he gets 2 talks, I figured I'll try to match him by doing 2 talks at the same time. One's going to be about math oxymorons, and one's going to be about names that are verbs. Names that are verbs appears at the bottom of each slide, and each slide has a math oxymoron in red, such as an accurate estimate in this first one, as you can see. And I think it is an accurate estimate to say you use these in your class. In fact, one might say in algebra class that 2 expressions are approximately equal. Well, are they equal, or is it approximate? What's going on there? Or which one is it? Anyone named Bob in the crowd? Hey, Bob, how you doing? Let's split some quantity into halves, like maybe this room. Let's split you into halves. We'll talk about the larger half. Have you done that in your math class? Is it a complete half? What about the smaller half? Is that a whole half? Any chips in the room? Not today. Okay, well, that last slide, by the way, I don't know if you got it or not, but the whole hemisphere was paying attention to that. Pat, I know Pat's here. Pat Riley, are you still here? There you are. Hey, Pat. How you doing? Good to see you. Don't go anywhere. You're coming up again. I really am starting to think this conversation on halves that we're having in the last 2 slides, it's a little straight out of line here. We might want to get this together. This line does extend to infinity and beyond. I was told this conference is in close proximity, whatever that means, to Chicago. I figured it's AMATYC anyway. There's no way I'm missing this. I only have one choice. I'm going. Any grants in the house? That's a rare name these days. No grants. There was a talk on grants earlier, different type of grants. Ignite is the one breakout in AMATYC where you could be sure the room will not be fully empty. That is true. Look at this full room. It's amazing. Any flips in the class? I was going to say in the house. By the way, I went to a Bucks game with 2 of my colleagues on Thursday night. Great experience. I'm confident that betting on them to win the East was a great thing to do at even odds this year. Well, those even odds are great. They pay well. By the way, them winning, that's an accurate prediction. It's very accurate, and it's a prediction at the same time. This conference rocks. Fuzzy logic I'm using, you might say. And, AMATYC's always consistently random, but always great. So, any Marks in the house? I'm sure there's some Marks in the house. It's a lot of names and verbs. Hey, Mark, how you doing? Did you think the slide was not going to have a name at the bottom? You must have been expecting a different pattern. It does have the name mark on there. Hey, Rob, are you still here? Rob Abbey, are you still in the house? He presented earlier. Oh, he called it at night. Okay. Well, did you think this slide was not going to have a math oxymoron because it started with Rob? False negative. Again, just a different pattern, guys. It's all good. We'll come back to the regular pattern pretty soon. As a matter of fact, after some random order on that last slide, we're now back to normal here. Welcome back. I promise no more sharp curves, okay? It's all straight from here. Speaking of, again, you might think of me as someone who's predictably rational due to these procedural variations in my presentation here. But again, it's just that fuzzy logic of yours coming back to haunt you. Don't let it bother you. It's all good. So, I wonder, how many gifts for us John Oakes brought to this presentation? There was an email chain about that. I hope the number is not a fixed variable. I really do. And I hope it's also not extremely average. John, did you bring any gifts for us? Anything for us to enjoy there? The 100% plus at this conference believe in united divisions when it comes to all branches of math. Do you guys? Yes? Do you believe in united divisions of math? No? You don't? You don't believe in that? Have you ever told your students to multiply by a denomination when they do currency conversion problems? I do it all the time. Any people named Grace in the room? I haven't met a Grace yet. And I'm not going to meet one tonight either. An infinitely finite number of math educators are gathering in AMATYC next year. Make sure you go there. I was far yet near from using an actual math example here, so I wanted to keep it straight. Carol's a great name. The season for that name's coming up, and I hope you enjoyed this relatively perfect presentation. Thank you.
Welcome back, Bruce.
Yeah, so actually, I did teach stats a few times early in my career, even though I've never taken a stats course. And since I've had to do that, I thought more a little bit about linear regression. And the way I think about it isn't the same way that was in the books that I taught from. The standard view is that the least squares regression line is the line that minimizes the squares of the vertical distances between data points and the line, and that the correlation coefficient R measures how tightly the points fit to that line, where they fit perfectly if R is plus or minus 1. But another way to think about R is that it's the cosine of an angle between two vectors in n-dimensional space. And that would imply that the R is 1 when the two vectors point in the same direction, negative when they point in opposite direction, and it's 0 when they're orthogonal. To get that, the physicist's idea of a dot product is the dot product gives you the magnitude of the first, magnitude of the second times cosine of the angle between them. And in any space you want with a dot product, you can define cosine of the angle of two vectors by cosine is that magnitude over the dot product with magnitude. So we do this by, you take all your x coordinates of your points, put it in one vector, all the y coordinates in another vector. I'll use that notation. I'll use x bar for the mean of x's, y bar for the mean of y's. And then you stick all of the x coordinates, x minus x bar, in one vector and put the y minus y bars in the other vector. And then when you compute the cosine theta by the dot product of those two vectors, you get exactly the correlation coefficient. And if nothing else, it's a nice mnemonic. All right, so if you wondered why you have to do these v's and w's and not work directly with x's and y's, well, if R is supposed to measure how well these line up, you'd want it to be the exact same value if you took all those data points and moved them horizontally just by 10 points. And you get that by adding 10 to each of the x coordinates. So, or by vector notation, to the x coordinate, you add an h times the vector of all ones. And if you want to ignore the effect of those horizontal translations, you want to just pay attention to what's called the orthogonal complement of that vector of ones. So yeah, we can take any vector and break it up into two pieces, one that's parallel to a given important direction and one perpendicular to it. And when you, well, yeah, you do it in physics all the time for force diagrams. So when you do that for lining things up with the one vector, you get that the parallel component is the vector that has all x means in it. And then you subtract that from the regular vector of x's to get the orthogonal complement. Now, what's kind of cool is that orthogonal complement's magnitude is almost exactly the standard deviation. All I have to do is take that magnitude and divide by the square root of n, and you've got the standard deviation. I just think that's another cool way of thinking about that particular statistics idea. All right, now when you want to find this least squares regression line, one way to think about solving that is you're trying to find two unknowns, m and b, so that mxi plus b gives you the y for all n data points. That's n equations and just two unknowns, which you can't solve. Slightly different way of thinking about it is you're solving this vector equation, unknowns m and b, and you want m times the x vector plus b times the one vector to be your y vector. You can't usually do that, but you can always solve for the projection of y into the span of the x vector and the one vector. And when you solve it, I thought this was cool, that the m turns out to be r times the ratio of the standard deviation of y over x. And the b is just exactly what you need so that the x mean, y mean point lies on your line. All right, so you might have seen this kind of statement that r squared gives you a fraction of a variance in y predicted by a straight line bit. All right, so we know that the m is r times the ratio of the sigmas. You square everything, and you get that the m squared times the variance in x is r squared times variance in y. And what you expect if y equals mxp for all the points, you'd expect that since x is scaled by m, that variance should be scaled by m squared. And that equation near the bottom shows what that other statement actually means. All right, I got this equation, thumbing through some statistics book. It had this innocuous looking equation that's clearly true no matter what the context. It had this little statement and this bizarre thing that looked horribly wrong. And it certainly didn't follow from just squaring and adding. But the way to see the way that works is you can translate that funny equation into this thing with vectors. And it's an equation saying that the sum of the squares of two norms is the square of another norm. And that works in this context because it works whenever the two things being added up, those two things are orthogonal vectors. And all right, so here's the proof that works for orthogonal vectors. if C is the sum of X and Y, A and B vectors, and you want to compute the squares of the norms and add them up, then you just keep track of the fact that dot of a vector times itself gives you back the square of the norm. And then everything just falls out really nicely. And that's the end of my talk. But if you wanted to just change the C to A minus B, you get a derivation of the law of cosines.
Hey, welcome back, Jennifer.
Thank you. This was so much fun to make, and it's very laid back. But I had this idea of what inspires you. And then for some people, it's what is your favorite quote. This is the first one I got back from my colleague. You can't go back and change the beginning, but you can start where you are and change the ending. C.S. Lewis, amazing. Confucius makes a couple of appearances. The person who says she can and the person who says she can't are both right. That was from my husband. So the random name on there is the person who gave me the quote. Attitude is the mind's paintbrush. It can color any situation. And Laura is the bridge between Jefferson and Bellarmine. She's worked at both, as I have. So that's really fun. Education does not transform the world. Education changes people. People change the world. Laid back, nice and easy. We're not gonna. Theodore Roosevelt makes a couple of appearances. Nobody cares how much you know until they know how much you care. In the classroom, students don't care how much you know until they know how much you care. Pat Riley making another guest appearance in a talk. Yay! Don't give up. Don't ever give up. Our HCC guests have been very helpful. This is from Arthur Schultz. Shoot for the moon. Even if you miss, you'll land among the stars. This is very sweet. Especially, we had a couple of NASA talks here. This one says, education costs money, but then so does ignorance. Thank you, Sherry, for that. So a lot of the people who sent me the quotes are actually here in the room tonight, which is just great. One of my colleagues, this is huge for us. If we teach today's students, as we taught yesterday's, we rob them of tomorrow. So for anyone who's done this for 30 years and want to keep doing the same thing for the next 30 years, it's food for thought. John Oakes, he follows me again, and he makes a special guest appearance. So Ben sent me this quote, and I said, well, who did you attribute it to? He goes, well, when I say it, the struggle is real. He's attributing it to John Oakes. Okay, so our first year experience coordinator, this is a really kind of good mental shift in our perspectives. Long-range planning does not deal with future decisions, but with the future of present decisions. I love Nora Ephraim. Venetia Lacey is our deaf and hard of hearing coordinator, very passionate woman. Your education is a dress rehearsal for the life you want to lead. Teddy Roosevelt again. Do what you can with what you have where you are. Adapted to the Arthur Ashe quote, start where you are, use what you have, do what you can. And Terry Letts is our artist, our resident artist. This is from my sister who teaches Japanese, has her humanities art PhD, and is the study abroad coordinator. You cannot get through a single day without having an impact on the world around you. What you do makes a difference. And I lost it. I can go back. Audre Lorde, without community, there is no liberation. That's from my sister who teaches English at Highline Community College out in Seattle. So, yeah. My sister is the science specialist. I hear and I forget. I see and I remember. I do and I understand. Confucius. Einstein's about to make an appearance. I just love this. I know it's kind of standard. It's been making the rounds on Facebook again. But basically, everybody is a genius. But if you judge a fish by its ability to climb a tree, it will live its whole life believing that it is stupid. And this is my dad. He's kind of on a World War I kick. Never have so many owed so much to so few. And I just invite you to put that in a different context than necessarily what it was originally said. And then this is my favorite quote. My dad, no good deed goes unpunished. And I don't know how many of you live that, but that's my life. John Oakes, you are up. Come on up.
Well, there's another meme from Pat Riley after this one. I don't know what I'm going to do. So you better get ready, Pat, because you might be up after me again. You never know. So this is about why I hate email. But, one time I had a student who could not open a Gmail account because her probation officer told her she could not have a Gmail account. So, this particular student really wanted an email account. So, this is one reason why I hate email, because pointless emails are always coming. You might be bracing yourself right now for winter, but pointless emails are year-round problems, right? So this is the one thing that I even hate even more, getting an email asking for my email address. Can't they just look for it? I mean, how do they even contact me? Can I get myself on the do not email list? And then this lady, this is the one coming up. You'll all recognize her, the one that sends the other reminder email, over and over and over again, like 5 reminders telling me that she forgot my email address and I need to send it to her again. Will you please send me your email address? Oh, yes. And then she sends me these very, very long emails. And I get really bored because, you know what? Emails are coming. So what am I going to do? Like, I have so many to read, and then comes another long one. And then guess what? That meeting that I survived could have been another email. So then even more emails come in. Can you absolutely believe that, Pat? Like, more emails of memes, Pat, and then pointless emails. And then when I actually do check my email, sometimes I don't check my email. And then when I do check my email, I've missed something really important. So what can I do? Like, I should go get this beer right now, right after this, right? And then there's these people, they're out there, like you in the hallway, walking right by. You're going to find me and you're going to send me an email. I know that you are. Yeah, don't ignore me over there. Yeah, come back where I can see you, and then I know that I can get you to send me an email asking me for my email address. And then, guess what? When they do send it to me, they send me another one because they might not even read it. Can you imagine this? Like, they might not even read my emails after they, ask me to email them over and over and over again. And then, guess what? This one is about your students here. All right, just wait for this one. The student asking about whether or not I got their email. Well, I was teaching in class, like at the end of class. Did you get my email? No, what do you think I was doing for the last 2 hours? Oh boy, well, maybe I was sending memes like Pat. And then, if people could just stop replying all to these emails, that would be great, don't you think? I mean, stop replying all, you two that just walked in, that's the worst thing that you can do. And except for this, responding to messages in all caps, or maybe not responding to messages in all caps, I don't know, but just don't do it. It's really, really bad. And then the last one, it might not be the last one, I have no clue, but, but when you forget to have the attachment, and then you reply all saying, I forgot the attachment. And then, guess what? This one will really, really get you. When you forget your password, I have a great tip for you. All right, you should set your password to be incorrect, so it tells you your password is incorrect. What can you do? Like, if you forget your password, now, if you forget your password and the email gets lost, maybe the email bounced. You can go in there and you check your spam folder and it's not there, so you think maybe it's bounced. The person didn't get me. Oh no, they're going to have to send me another email. And then guess how many emails you're going to have? Anyone have a ballpark number? Over 3.5 million emails in your spam folder. This is where the stress comes from. And then not only the emails you have to check, You have to check emails, you have to read them, you have to do all of that. But sometimes they ask you to send more of them. Can you imagine that? Like, can you send me an email reminding me about something? Why can't you just write it down and remind yourself, ladies? This one lady come by my office, like, will you send me an email about that? Just make a note of it. And then, how did this lady get this email when they might not even deliver on Sundays? Oh no, she checking, is it Sunday? Oh no, my emails might not be coming in until Monday. But I mean, you know what? That's what I would really like, except for you to please not send me any more email. And by the way, I hate text messages just as much, so don't send me those. Don't call me. Put my computer by the curb so that, oh, by the way, trash day is on Thursday, so if you want to put it by the curb so I don't get any more emails from you, that would be great.
Round of applause to Johnny and all our presenters tonight. We're still full. Thank you for sticking around. Thank you for enjoying the Ignite event. Think about applying and sending me an email to speak at next year's Ignite in Spokane. Thank you so much. Thank you all the audience. Thank you, Maria, for volunteering your laptop. Now let's go drink some beers.
Everybody can see. It worked.
Hey, Fred, let's get a picture of everybody up on.
Oh, all the presenters come up to the stage for a picture. If you're still here, presenters, come up to the stage for a picture. If you're still here, presenters, come up to the stage.